There are at least 11 billion Earth-sized planets sitting in the habitable zones of stars in our galaxy alone. 11 billion chances for oceans, atmospheres, and maybe even minds staring back at the sky the way you are right now. And yet, silence, no signal, no visit. No proof that anyone out there has ever known we exist. Most people assume the problem is rarity. Maybe life is just too hard to start. But what if that is not the problem at all? What if life is everywhere and it does not matter? What if the universe is built, from its deepest physical foundations, to make sure that no two civilizations ever meet? The truth is not that aliens are impossible. The truth is far worse than that. If you enjoy having your entire understanding of the cosmos shaken to its core, do me a small favor, hit that like button and subscribe. It really does help more than you know, and I genuinely appreciate every single one of you. Now, get yourself comfortable. Let's begin. Every child who has ever looked up at a night sky full of stars has felt the same instinct. Somewhere out there, someone is looking back. The feeling is so natural, so deeply embedded in the way humans process the cosmos, that most people never stop to question whether it is justified. We see a universe overflowing with stars. We learn that planets orbit most of those stars. We hear scientists describe billions of potentially habitable worlds scattered across our galaxy, and our brains do what they were designed to do. They connect the dots. They draw a line from possibility to inevitability. If there are that many chances for life, then life must exist. And if life exists, then one day, surely, we will meet it. This expectation is everywhere. It lives in the way governments fund space telescopes. It breathes through every science fiction film where humans shake hands with beings from another star. It drives the search for extraterrestrial intelligence, a project that has been listening to the cosmos for over 60 years, scanning radio frequencies across the sky with the patient faith that someone, somewhere, is transmitting. The belief that alien contact is only a matter of time has become so deeply woven into modern culture that questioning it feels almost irrational. Of course we will meet aliens. The universe is too big and too old for us to be alone. The math practically demands it. But here is the thing about that math. It is built on an assumption so fundamental that almost nobody notices it hiding in the equation. The assumption is this: if aliens exist, then meeting them is a solvable problem. Find the right frequency, build the right telescope, wait long enough, travel far enough. The existence of alien life and the encounter with alien life are treated as 2 points on the same timeline, separated only by effort and patience. This assumption feels so obvious that it has never needed defending. It simply sits there, invisible, shaping every conversation humanity has ever had about its place in the cosmos. And it may be completely, catastrophically wrong. Before we confront why, it is worth understanding just how reasonable the expectation appears on the surface, because the numbers really are staggering. As of early 2026, NASA's Exoplanet Archive lists over 6,150 confirmed planets orbiting stars beyond our solar system. 6,000 worlds, each one a real place with a real orbit around a real star. Some of these planets are gas giants larger than Jupiter, baking in radiation close to their parent stars. Others are rocky, Earth-sized, orbiting at distances where liquid water could theoretically persist on their surfaces. And these 6,000 represent only what we have found so far, using instruments that can only detect a tiny fraction of the planets that actually exist. The real numbers dwarf the catalogue. Astronomers estimate that roughly 1 in 5 Sun-like stars hosts an Earth-sized planet in its habitable zone, the orbital region where temperatures permit liquid water on a rocky surface. The Milky Way contains somewhere between 100 billion and 400 billion stars. Even using conservative estimates, the galaxy harbours at least 11 billion potentially habitable Earth-sized worlds orbiting Sun-like stars alone. Expand the count to include planets orbiting red dwarf stars, the most common stellar type in the galaxy, and the number climbs toward 40 billion. 40 billion possible Earths in one galaxy, in a universe containing approximately 2 trillion galaxies. These are not speculative figures pulled from science fiction. They come from the Kepler Space Telescope's systematic survey of over 150,000 stars, from the Transiting Exoplanet Survey satellite's ongoing scan of the entire sky, from decades of radial velocity measurements painstakingly gathered by ground-based observatories around the world. The planetary abundance of the Milky Way is one of the most firmly established facts in modern astronomy. Planets are not rare. They are everywhere. The galaxy is saturated with worlds, and the conditions for life appear far less restrictive than scientists once believed. Water, the solvent that enables the biochemistry we understand, is one of the most abundant molecules in the universe. Carbon, the backbone of organic chemistry, forms in the nuclear furnaces of every massive star and gets scattered across space when those stars explode. The basic molecular ingredients for biology, amino acids, sugars, nucleobases, have been found in meteorites and interstellar dust clouds. Complex organic chemistry thrives even in the atmosphere of Titan, a moon orbiting Saturn. The chemistry of life is not exotic. It is woven into the fabric of cosmic evolution. The universe manufactures the raw materials for biology as a natural byproduct of stellar death. Life on Earth appeared remarkably quickly. The planet formed approximately 4.5 billion years ago. Within its first few 100 million years, possibly as early as 4 billion years ago, microbial life had already taken hold. The geological record suggests that once conditions became even remotely tolerable, life did not hesitate. It emerged almost immediately on cosmic timescales, as if the transition from chemistry to biology was not a miraculous accident, but an expected outcome of certain physical conditions. If that pattern holds elsewhere, if life tends to appear quickly once the right conditions exist, then the sheer number of habitable worlds in the galaxy makes a lifeless Milky Way seem almost impossible. This is the foundation of what might be called the great cosmic optimism. The ingredients are common. The environments are abundant, the timeline is generous, everything points toward a galaxy teeming with life. And from that conclusion, the human mind takes one more step, the step that feels so natural it barely registers as a leap. If life is out there, we should be able to find it. And if we can find it, we should eventually be able to meet it. Science fiction cemented this leap into cultural bedrock. The genre did not merely entertain the idea of alien contact. It made contact feel inevitable, almost routine. From the earliest days of radio-era imagination, stories about life beyond Earth almost always arrived at the same destination: the meeting. Sometimes it was peaceful, a handshake across species, a sharing of knowledge that elevated both civilizations. Sometimes it was hostile, an invasion, a war, a fight for survival against beings whose motives were alien but whose physical presence was undeniably real. The tone varied, but the underlying premise never did. If aliens exist, they will show up. The only question was when and how. Consider how deeply this assumption runs. In nearly every major science fiction franchise of the past century, interstellar travel is treated as an engineering challenge that advanced civilizations have solved. Ships cross between stars in days or weeks. Communication happens in real time across light years. Species from different corners of the galaxy meet in bars, argue in councils, wage wars across sectors of space. The dramatic tension is never about whether contact is possible. It is always about what happens after contact occurs. The audience is never asked to consider the possibility that the meeting itself might be the impossible part. This narrative architecture trained generations to think about the cosmos in a very specific way. The universe became a neighborhood. Stars became destinations. The question shifted from whether alien life exists to what alien life looks like, what it wants, how it thinks. Entire branches of speculative thought, from astrobiology to exopolitics, grew from the unexamined assumption that existence implies encounter. The emotional logic was irresistible. A universe full of life must be a universe full of connection. Loneliness at the cosmic scale seemed like a temporary condition, a problem that better technology would eventually solve. Even serious science absorbed this framing. The Drake equation, formulated in 1961 by astronomer Frank Drake, attempted to estimate the number of communicative civilizations in the Milky Way. The equation multiplies a series of factors: the rate of star formation, the fraction of stars with planets, the fraction of planets where life develops, the fraction of life that becomes intelligent, the fraction that develops detectable technology, and the average lifespan of such civilizations. Each variable represents a genuine uncertainty, but the equation's structure carries an implicit promise. It suggests that contact is a numbers game. Get enough civilizations, and communication becomes statistically likely. The equation does not ask whether communication is physically possible across galactic distances. It assumes it is and asks only how many partners are available. This subtle framing shaped decades of scientific thought. The search for extraterrestrial intelligence began in 1960 with Project Ozma, which pointed a radio telescope at two nearby stars and listened for artificial signals. The search has continued in various forms ever since, growing more sophisticated with each generation of technology. Modern SETI programs scan millions of star systems simultaneously, covering wide swaths of the radio and optical spectrum. The Allen Telescope Array, the Breakthrough Listen Initiative, and dozens of smaller programs collectively represent one of the longest sustained scientific searches in human history. And the underlying logic has never wavered. Alien civilizations should produce detectable signals. We should be able to find those signals if we listen carefully enough. Contact is out there, waiting for us to tune to the right frequency. But after more than 6 decades of searching, the result is silence. Not ambiguous silence. Not almost silence punctuated by tantalizing hints. Silence. Total, complete, unbroken cosmic quiet. No confirmed artificial signal has ever been detected from any star system beyond our own. No alien transmission has been identified in any wavelength. No probe, no artifact, no structure, no waste heat signature, nothing that unambiguously indicates the presence of technological intelligence anywhere in the observable universe. This silence has a name. It is called the Fermi Paradox, after physicist Enrico Fermi, who reportedly asked his colleagues over lunch in 1950 a question that has haunted science ever since. If the galaxy is so old and so vast and so full of stars and planets, where is everybody? The question was casual, its implications were not. Fermi grasped something that the optimistic framework tends to obscure. The galaxy is more than 13 billion years old. Even at modest speeds, a civilization that decided to spread across the stars could colonize the entire Milky Way in a few tens of millions of years, a geological blink. The galaxy has had enough time for this to happen thousands of times over. And yet, no evidence of galactic colonization exists. No alien megastructures dim distant stars. No self-replicating probes orbit our sun. No ancient visitors left artifacts on the Moon or Mars. The Fermi Paradox has generated dozens of proposed solutions over the decades, and most of them focus on why alien civilizations might not exist, or why they might exist but choose to remain hidden, or why they might exist but inevitably destroy themselves before achieving interstellar reach. The zoo hypothesis suggests advanced aliens are watching us but deliberately avoiding contact. The dark forest hypothesis, popularized by science fiction author Lou Sixin, proposes that civilizations stay silent because revealing your position invites annihilation from hostile competitors. The Great Filter theory suggests that somewhere along the path from simple chemistry to interstellar civilization, there is a barrier so difficult that almost nothing gets through. Perhaps the filter is behind us, meaning life or intelligence is vanishingly rare. Perhaps it is ahead of us, meaning technological civilizations tend to destroy themselves. Each of these explanations carries a certain dramatic weight. They imagine alien minds making choices, civilizations rising and falling, cosmic dangers lurking in the dark. They are fascinating as thought experiments. But they all share a common feature that deserves scrutiny. They all assume that if a civilization survives long enough and develops the right technology, contact with other civilizations is physically achievable. The problem in every one of these frameworks is either scarcity of civilizations or behavior of civilizations. The universe itself is treated as a neutral stage, a vast but ultimately navigable space where minds can, in principle, reach one another. But what if the universe is not neutral? What if the problem is not how many civilizations exist or what choices they make? What if the problem is the universe itself, the actual physical structure of space, time, and causality, engineered by no one, but functioning as an absolute barrier between every mind that has ever existed or ever will? This is the distinction that changes everything. The difference between alien existence and alien encounter. Two concepts that sound almost identical but are separated by a chasm so vast that most people never notice it is there. Existence asks a biological question. Can the chemistry of life arise on other worlds? The evidence suggests yes, probably many times, probably across billions of planets. Encounter asks a physical question. Can two civilizations that arise independently on different worlds, separated by light years or tens of light years or thousands of light years, ever exchange a single meaningful piece of information? Ever confirm each other's existence in real time? Ever stand in the same room or orbit the same star? Or share a single moment of mutual awareness? These are fundamentally different problems, and the universe treats them with fundamentally different levels of generosity. The cosmos is extraordinarily hospitable to the emergence of life. It manufactures habitable planets by the billion. It seeds space with organic chemistry. It provides billions of years of stellar stability for evolution to operate. But the same cosmos is extraordinarily hostile to the meeting of life. It separates stars by distances so vast that light itself requires years to cross them. It imposes a universal speed limit that no amount of technology can overcome. It ensures that even the closest potentially inhabited worlds are divided by gulfs that would take current spacecraft tens of thousands of years to traverse. The universe gives with one hand and takes with the other. It fills the galaxy with the conditions for life while simultaneously building walls between every place where life might arise, and the walls are not engineering problems waiting for clever solutions. They are woven into the geometry of space-time itself, into the fundamental constants that govern how fast information can travel and how far matter can reach. A survey published in Nature Astronomy found that over 87% of scientists in relevant fields believe at least basic extraterrestrial life exists somewhere beyond Earth. More than 67% believe intelligent aliens are out there. The scientific community has largely accepted that we are probably not alone. But believing that life exists somewhere is profoundly different from believing that life can be reached. The first belief is supported by chemistry, by statistics, by the sheer abundance of habitable real estate the universe provides. The second belief is supported by almost nothing except human intuition and the narrative conventions of science fiction. When you watch a film where a starship jumps to another solar system in seconds, your brain files that experience alongside real knowledge. It becomes part of your mental model of the cosmos. The emotional residue of that scene sits in the same cognitive space as the factual knowledge that exoplanets exist. Over time, the boundary between what is physically real and what is dramatically convenient blurs. The idea that we could travel to another star system begins to feel not like fantasy, but like a future inevitability. We just need better engines. We just need more time. We just need to want it badly enough. But wanting something has never changed the laws of physics. And the laws of physics have something very specific to say about whether two civilizations arising on different worlds around different stars can ever bridge the gap between them? The answer is not encouraging. It is not a matter of pessimism or optimism. It is a matter of what space and time actually are, how they behave, and what they permit. What comes next will take you inside that answer. It will show you exactly what stands between humanity and the alien civilizations that may, right now, be looking up at their own night sky and wondering the same thing we wonder. The barrier is not silence. It is not absence. It is structure. The universe is built a certain way, and that architecture has consequences that most people have never been forced to confront. Everything you have been told about meeting aliens, every assumption you carry, every hopeful expectation planted by decades of stories and speculation rests on a foundation that physics does not support. The beautiful lie is not that aliens exist. They very well might. The beautiful lie is that existence means we will ever know. The walls are real, and they are far taller than anyone has told you. Let us start with the nearest star. Not the nearest interesting star. Not the nearest star likely to host life. Just the nearest star, period. Proxima Centauri sits approximately 4.24 light-years from Earth. In the vocabulary of astronomy, that number sounds almost intimate. 4 light-years, a small number, a number you could hold in your hand. But the language of light-years is a kind of camouflage. It wraps impossible distances in tidy packaging and tricks the brain into thinking they are manageable. So let us unwrap it. 1 light-year is the distance that light, moving at approximately 186,000 miles per second, covers in a single year. That works out to roughly 5.88 trillion miles. Multiply that by 4.24 and the distance to Proxima Centauri reveals itself. Approximately 25 trillion miles. 25 followed by 12 zeros. A number so large that writing it out in full would fill a line across this screen and still mean absolutely nothing to the human brain. Our minds evolved to judge the distance between trees, between predators, between one water source and the next. We have no neural architecture for processing trillions of miles. The number enters the mind and simply collapses into a vague sense of far. So let us make it concrete. Voyager 1, launched in 1977, is the fastest object humanity has ever sent into interstellar space. It travels at roughly 38,000 miles per hour. At that speed, it covers nearly 1 million miles every single day. Voyager 1 is currently the most distant human-made object in existence, sailing through the interstellar medium beyond the influence of our sun's magnetic field. It has been traveling for nearly 5 decades, and in all that time, at all that speed, it has covered a distance equal to less than 0.1% of the gap between our Sun and Proxima Centauri. If Voyager 1 were aimed directly at the nearest star, which it is not, it would arrive in approximately 73,000 years. 73,000 years. Human civilization in its entirety, from the first crude settlements in Mesopotamia to the phone or screen you are using right now, spans roughly 5,000 years. Voyager would need to fly for more than 14 times the length of recorded human history to reach the closest star in the sky. And Proxima Centauri is right next door. It is our stellar neighbour, the nearest address on the nearest street in our galactic city. The Milky Way stretches approximately 100,000 light-years from edge to edge. Most of the stars in our galaxy are separated from us not by 4 light-years, but by tens of thousands of light-years. The galactic centre lies roughly 26,000 light-years away. Stars on the far side of the Milky Way sit 100,000 light-years distant. At Voyager's speed, crossing the full diameter of the galaxy would require approximately 1.7 billion years. The galaxy is so vast that our fastest spacecraft would need longer than the age of complex multicellular life on Earth just to traverse it. These distances are not incidental features of the cosmos. They are the defining reality of interstellar space. The average separation between neighbouring stars in our region of the galaxy is roughly 4 to 5 light-years. In the denser regions near the galactic centre, Stars crowd closer together, perhaps a light year or two apart. In the sparse outer arms where our solar system resides, the gaps widen. But even in the most crowded neighborhoods of the Milky Way, individual stars are separated by trillions of miles of functionally empty vacuum. Space between the stars is not merely big. It is a void so absolute that a single atom of hydrogen per cubic centimeter counts as dense by interstellar standards. If you shrank the Sun to the size of a ping-pong ball and placed it on a table, the nearest star at that scale would be another ping-pong ball sitting roughly 700 miles away. Everything between them would be empty. Absolutely, perfectly, terrifyingly empty. This emptiness matters because it defines what is physically possible. Crossing interstellar distances is not like crossing an ocean or a continent. Those journeys are difficult, but the medium is continuous. You can stop, rest, resupply, change course. Interstellar space offers nothing. No fuel, no shelter, no way stations, no landmarks, just vacuum stretching in every direction for trillions of miles. Any vehicle attempting the crossing must carry everything it will ever need for the entire journey, or it must find a way to collect resources from the near-perfect nothingness between stars. Neither option is trivial. Both are, with current and foreseeable technology, effectively impossible at any meaningful scale. But distance alone is only half the problem. The other half is speed. And the speed limit of the universe is not a suggestion. It is a law, one of the most thoroughly tested and rigorously confirmed laws in all of physics. And it has consequences that dismantle nearly every intuitive hope humans carry about reaching other stars. Nothing that has mass can travel at the speed of light. This is not a technological limitation. It is not an engineering challenge waiting for a breakthrough. It is a geometric property of space-time itself, encoded in Einstein's special theory of relativity and confirmed by over a century of experimental evidence. As an object with mass accelerates, the energy required to increase its speed grows, not linearly, not even steeply. It grows without bound. The closer you get to the speed of light, the more energy each tiny increment of additional speed demands. At 90% of light speed, you need vastly more energy than at 50%. At 99%, vastly more still. At 99.9%, the energy requirement skyrockets again. To actually reach light speed, you would need infinite energy. Not the energy of a star, not the energy of a galaxy. Infinite energy, the kind that does not exist anywhere in the physical universe, not in any quantity, not in any form. This is worth pausing on because the implications are absolute. It does not matter how advanced a civilization becomes. It does not matter if they have had 1 billion years of technological development. It does not matter if they harness the full energy output of their star, or their galaxy, or 100 galaxies. The speed of light cannot be reached by any object with mass, and it cannot be exceeded. Einstein's equations apply everywhere. They apply to humans, to hypothetical aliens, to any civilization constructed from matter and energy in this universe. The light speed barrier is not a wall that cleverness can find a door through. It is the shape of reality itself. Science fiction has spent decades inventing workarounds. Warp drives that compress space in front of a ship and expand it behind. Wormholes that connect distant points through higher dimensional shortcuts. Hyperspace, subspace, jump drives, fold drives. These concepts are narratively convenient and physically baseless. The Alcubierre warp drive, the most mathematically serious of these proposals, requires exotic matter with negative energy density, a substance that has never been observed and may not exist. Even if it did exist, the energy requirements for a functional warp bubble have been calculated at levels exceeding the mass energy of entire planets or stars. Wormholes, predicted by general relativity as mathematical solutions, would require conditions so extreme and so precisely maintained that no known physical process could create or stabilize them. Every serious analysis of faster-than-light concepts ends in the same place. The energy requirements are prohibitive, The physical mechanisms are speculative or impossible, and the laws of physics as we understand them simply do not permit it. This means that any civilization anywhere in the universe, no matter how intelligent, no matter how advanced, is confined to travelling at some fraction of the speed of light. And travelling at a fraction of light speed through interstellar distances produces journey times measured not in hours or days, but in years, decades, centuries, or millennia. Let us be generous. Let us imagine a civilization capable of travelling at 10% of the speed of light. This is far beyond anything humanity can currently achieve. Our fastest spacecraft moves at roughly 0.006% of light speed. 10% represents an increase of more than 1,000-fold, requiring propulsion technologies that do not yet exist and energy sources we have not yet learned to harness. But let us grant it. At 10% of light speed, the journey to Proxima Centauri takes approximately 42 years. That is a human lifetime devoted to reaching one star. The next nearest Sun-like star system, Alpha Centauri A and B, is roughly the same distance. After that, the gaps widen. Barnard's star sits 6 light-years away. A journey at 10% of light speed takes 60 years. Wolf 359 is nearly 8 light-years distant, 80 years. Sirius, one of the brightest stars in our sky and a fixture of human mythology since antiquity, lies 8.6 light-years away, 86 years, and these are the closest stars. The nearest known potentially habitable exoplanet, Proxima Centauri b, orbits the nearest star. But most of the 11 billion estimated habitable zone planets in the Milky Way are scattered across the full breadth of the galaxy. The average distance to a randomly selected habitable world is not 4 light-years. It is thousands of light-years. At 10% of light speed, a journey of 1,000 light-years takes 10,000 years. A journey across the galaxy takes 1 million years. These are not engineering timescales. These are geological timescales. They exceed the lifespan of civilizations, the lifespan of species, and in some cases the lifespan of the stars themselves. Now layer on the rocket equation, and the picture becomes even bleaker. Konstantin Tsiolkovsky formulated the fundamental equation of rocketry in 1903, and its logic is merciless. To accelerate, a spacecraft must expel mass. The faster you want to go, the more mass you must expel. But carrying more fuel increases the total mass of the ship, which means you need even more fuel to accelerate that additional mass. The relationship is exponential. For chemical rockets, the fuel-to-payload ratio required for interstellar velocities is not merely impractical, it is absurd. Reaching even 1% of light speed with chemical propulsion would require a fuel mass greater than the mass of the observable universe for any reasonably sized payload. The numbers do not merely fail to close, they explode into meaninglessness. Advanced propulsion concepts improve the situation but do not escape the equation's grip. Nuclear pulse propulsion, which detonates small nuclear devices behind the spacecraft, could theoretically achieve perhaps 3 to 5% of light speed. Fusion drives, if they can ever be built, might push that to 10 or 15%. Antimatter engines, which convert mass directly into energy with perfect efficiency, offer the highest theoretical performance. But producing antimatter in useful quantities is currently beyond any known technology. The total amount of antimatter ever produced by all particle accelerators on Earth combined amounts to a few nanograms, enough to heat a cup of coffee, not to propel a starship. Scaling antimatter production to the kilograms or tons required for interstellar propulsion would consume more energy than human civilization currently generates in centuries. But suppose a civilization solves the propulsion problem. Suppose they find a way to accelerate a ship to a significant fraction of light speed, say 50 or even 90%. Science fiction treats this as the finish line. The engines work. The ship flies. The crew arrives. Story over. But physics has another card to play. and it is one of the strangest and most disorienting consequences of Einstein's relativity: time dilation. The faster you travel, the slower time passes for you relative to everything you left behind. This is not a theory awaiting confirmation. It has been measured in laboratories, verified with atomic clocks aboard aircraft and satellites, and confirmed to extraordinary precision by particle accelerators. Time dilation is as real as gravity, and its implications for interstellar travel are devastating in ways that most people have never considered. At low speeds, the effect is negligible. A car on a highway, a jet crossing an ocean, even a spacecraft orbiting Earth, all experience time dilation so tiny that it only matters for ultra-precise instruments like GPS satellites. But as you approach the speed of light, the effect grows dramatically. At 50% of light speed, time aboard the ship passes roughly 13% slower than time on Earth. At 90%, the dilation factor climbs to about 2.3, meaning that for every year experienced by the crew, 2.3 years pass back home. At 99% of light speed, the factor reaches approximately 7. At 99.9%, it exceeds 22. This sounds like it might be helpful. If time passes more slowly for the travellers, they experience the journey as shorter. A trip to a star 100 light-years away at 99% of light speed takes approximately 101 years, as measured by clocks on Earth. But for the crew aboard the ship, only about 14 years pass. They step off the vessel feeling like they've been away for a decade and a half. They are met by a planet where a full century has elapsed. Everyone they knew is dead. The political systems they left behind have transformed or collapsed. The language may have shifted. The technology has certainly changed. The culture that launched them no longer exists in any recognizable form. This is not a side effect of interstellar travel. It is the central, unavoidable consequence. Relativistic travel does not merely move people through space, it moves them through time. A crew that departs Earth and accelerates to near light speed becomes temporarily severed from the civilization that sent them. They are not explorers returning with news. They are time travelers arriving in a future that does not remember them. The emotional and practical implications of this severing are so profound that they undermine the entire concept of interstellar contact as most people understand it. Consider what contact means. It means two civilizations exchanging information, learning from one another, establishing a relationship that persists over time. It means ambassadors who return to report what they found. Scientists who share discoveries with their home institutions. Cultures that evolve together through mutual exposure. All of this requires temporal continuity. The people who leave must return to a world that is still connected to the one they departed. Relativistic travel destroys this continuity. Absolutely. The travelers and the civilization that sent them diverge in time the moment the engines ignite. They can never fully reunite because they are no longer living in the same temporal frame. Even if you imagine a civilization so advanced that individual lifespans are no longer a constraint, the problem persists at the civilizational level. A ship sent to a star 1,000 light-years away, at 99% of light speed arrives in approximately 1,010 Earth years. The crew experiences roughly 140 years, but the home civilization has aged by a millennium. 1,000 years of political change, technological development, cultural evolution, and possible extinction. The ship that arrives at the distant star carries the values and knowledge of a civilization that no longer exists. It is an archaeological artifact travelling at relativistic speed, delivering the past to a present that has moved on. This temporal exile applies equally to any alien civilization attempting interstellar travel. Even a species that has mastered propulsion at a level we can barely imagine still faces the same relativistic mathematics. Their travellers still become disconnected from their origin. Their missions still arrive in futures that bear no resemblance to the era that launched them. The speed of light does not merely limit how fast you can go. It ensures that going fast enough to make interstellar travel survivable within individual lifetimes simultaneously makes it meaningless as a tool for civilizational contact. The universe offers a cruel bargain. You can cross the distance, but only by sacrificing your connection to everything you left behind. And even this assumes the travelers survive the journey, which introduces the final physical constraint that operates below the level of grand equations and cosmic geometry: biology. Living things are fragile. They are fragile in ways that no amount of technology has yet been able to fully overcome, and the interstellar environment is hostile to biological systems in ways that make even the harshest environments on Earth seem benign. The primary threat is radiation. Beyond the protective cocoon of Earth's magnetosphere and the Sun's heliosphere, interstellar space is saturated with cosmic rays, high-energy particles accelerated to near light speed by supernova explosions, neutron star collisions, and the violent cores of distant galaxies. These particles consist mostly of protons and atomic nuclei traveling with enormous kinetic energy. The most energetic cosmic ray ever detected carried as much energy as a baseball thrown at 60 miles per hour, all concentrated into a single subatomic particle. When these particles pass through biological tissue, they shatter DNA, damage cellular machinery, and create cascades of secondary radiation that compound the harm. On Earth, the atmosphere absorbs most cosmic rays before they reach the surface. Astronauts aboard the International Space Station, orbiting just 250 miles overhead, already receive radiation doses roughly 60 times higher than ground level. On a voyage lasting decades or centuries through unshielded interstellar space, the cumulative radiation exposure would be catastrophic. Current shielding technology can reduce, but not eliminate the dose. The most effective shields require massive amounts of material, which conflicts directly with the rocket equation's demand for minimal mass. A ship heavy enough to fully shield its crew from cosmic radiation would be too heavy to accelerate to useful speeds. A ship light enough to reach interstellar velocities would leave its occupants exposed to a slow, relentless bombardment of ionizing radiation that degrades biological systems over time. The problem compounds at relativistic speeds. A ship traveling at a significant fraction of light speed collides with interstellar hydrogen atoms and dust particles that, from the ship's reference frame, are approaching at tremendous velocity. Each hydrogen atom becomes a tiny projectile carrying relativistic kinetic energy. At 50% of light speed, these impacts generate damaging radiation, equivalent to standing near a particle accelerator beam. At 90%, the flux becomes lethal without shielding so massive it defeats the purpose of the journey. The interstellar medium, which is nearly a perfect vacuum by terrestrial standards, becomes a wall of radiation when you try to fly through it fast enough to reach another star within a human lifetime. Machines fare better than biology, but not as well as popular imagination suggests. Electronics degrade under cosmic ray bombardment. High-energy particles can flip individual bits in computer memory, corrupt data, and damage semiconductor junctions. Over timescales of centuries or millennia, even hardened electronics accumulate enough radiation damage to malfunction. Moving parts wear. Lubricants evaporate in vacuum. Seals degrade. Entropy, the universal tendency of ordered systems to decay toward disorder, operates on every physical structure with patient, relentless certainty. A robotic probe launched on a 10,000-year voyage to a distant star must maintain functional integrity across a span of time longer than the entirety of recorded human history. No machine humanity has ever built comes close to this requirement. The longest operating human spacecraft, Voyager 1 and 2, have been functioning for less than 50 years and are already experiencing system degradation that limits their capability. The interstellar medium itself poses risks beyond radiation. Dust grains, each one microscopic, become devastating projectiles at relativistic velocities. A grain of interstellar dust weighing less than 1/millionth of a gram strikes a ship traveling at 10% of light speed with the energy of a small explosive charge. At higher velocities, the energy scales quadratically. A speck that would be invisible to the naked eye hits with the force of a bomb. Shields can deflect some of this debris, but no physical shield can protect against every particle across a journey spanning light years of dusty interstellar space. The cumulative effect of billions of microscopic impacts over decades erodes hull material, degrades sensors, and threatens structural integrity. Every physical system, biological or mechanical, faces the same fundamental reality. The interstellar environment is not a benign vacuum waiting to be crossed. It is a gauntlet of radiation, particle bombardment, and relentless entropy that attacks travelers at every moment of a journey, lasting years, decades, or millennia. The longer the journey, the more damage accumulates. The faster the ship, the more hostile the medium becomes. There is no speed at which interstellar travel becomes both fast enough to be meaningful and safe enough to be survivable, without technologies that do not currently exist and may not be physically possible. At this point, a reasonable person asks the obvious question. If fast travel fails because of physics and biology, what about going slowly? What about building a ship large enough to sustain a human population for centuries or millennia? A self-contained world crossing the void between stars at a modest fraction of light speed, arriving not with the crew that departed but with their distant descendants. The generation ship is one of the oldest and most persistent ideas in interstellar travel. It appears in science fiction with the regularity of a recurring dream, and it deserves a serious answer, because the answer reveals why slow travel fails for reasons that have nothing to do with physics and everything to do with what civilizations actually are. A generation ship bound for a star 100 light-years away at 1% of light speed faces a journey lasting 10,000 years. The ship must sustain a breeding population of humans across roughly 400 generations. It must provide food, water, breathable air, medical care, education, governance, and psychological stability for every one of those generations. It must maintain its own structural integrity, its propulsion systems, its navigation, its life support, and its hull against the cumulative degradation of micrometeorite impacts and cosmic radiation across a span of time twice as long as recorded human history. And it must do all of this as a closed system, with no resupply, no external repair, no contact with any civilization or infrastructure beyond its own walls. No human institution has ever sustained itself for 10,000 years. The oldest continuous civilizations on Earth, measured by cultural or political continuity, span perhaps 4,000 or 5,000 years at most, and even those have undergone transformations so radical that their founders would not recognize them. Languages mutate, religions schism, political structures collapse and reform, technologies are lost and reinvented. The idea that a closed population of a few thousand people, sealed inside a metal cylinder drifting through the void, could maintain cultural coherence, technical competence, and mission focus across 10,000 years requires a faith in human nature that nothing in the historical record supports. The sociological challenges alone are staggering. Isolation experiments on Earth, even those lasting only months or a few years, consistently produce psychological stress, interpersonal conflict, group fragmentation, and institutional breakdown. The Mars 500 experiment, which confined 6 volunteers in a simulated spacecraft for 520 days, documented significant psychological deterioration, sleep cycle disruption, and social withdrawal even within that brief period. Scale this to centuries, and the problem does not merely grow. It transforms into something qualitatively different. The people born on a generation ship did not choose to be there. They inherit a mission conceived by ancestors they never met, aimed at a destination they will never see. The intermediate generations, those born too late to remember Earth and too early to reach the target star, live their entire lives inside a metal container for no reason they personally endorsed. The potential for resentment, rebellion, cultural drift, and outright abandonment of the mission is not speculative. It is sociologically predictable. Then there is the technical problem of maintaining a closed-loop life support system. Earth's biosphere is the only self-sustaining life support system known to exist, and it required billions of years of evolution, a planet-sized surface area, and a continuous energy input from the Sun to achieve stability. The most ambitious closed ecology experiment ever attempted on Earth, Biosphere 2 in Arizona, failed within 2 years. Oxygen levels dropped dangerously. Carbon dioxide fluctuated. Crop yields fell short. Insect populations collapsed while ant and cockroach populations exploded. The system could not maintain equilibrium at any scale remotely comparable to what a generation ship would require. No closed life support system has ever been sustained for more than a few years without external intervention. Sustaining one for 10,000 years with no possibility of external resupply is not an engineering challenge awaiting a solution. It is a demand that exceeds anything human technology or biological science has demonstrated. The genetic dimension adds another layer. A breeding population confined to a few thousand individuals for hundreds of generations faces genetic drift, inbreeding depression, and loss of genetic diversity. Without active genetic management across millennia, the population's health and adaptive capacity would decline. Managing this requires biotechnological sophistication maintained flawlessly across 400 generations, a requirement that circles back to the institutional stability problem. If the society on the ship fractures, if knowledge is lost, if the biotechnological infrastructure fails even once across 10,000 years, the genetic consequences become irreversible. The generation ship is not a solution to interstellar travel. It is a restatement of the problem in biological and sociological terms. Fast travel fails because physics will not permit it. Slow travel fails because civilizations cannot sustain themselves in isolation across the timescales required. The universe closes both doors. Speed is capped by relativity. Endurance is capped by the fragility of complex social and biological systems. There is no pace of interstellar travel that is simultaneously fast enough to be completed within a civilization's lifespan and slow enough to be physically survivable. The gap between what physics allows and what biology and society can endure has no overlap region. It is a void, and no ship, fast or slow, can cross it. Laser sail concepts, like the Breakthrough Starshot initiative proposed in 2016, attempt to sidestep the rocket equation entirely by leaving the fuel at home. A powerful ground-based laser array would accelerate a tiny, lightweight sail to perhaps 20% of light speed. The concept is elegant, the constraints are savage. The sail must be extraordinarily thin and light. The payload must be minuscule, perhaps a few grams, enough for a microchip camera but not for a human being, not for a habitat, not for anything that could meaningfully represent a civilization making contact. And the sail cannot decelerate. It flies past its target star at 20% of light speed, gathering a few seconds of data during its closest approach before sailing on into the void forever. This is not a mission of contact. It is a message in a bottle thrown at tremendous speed across an ocean with no shore. There is a concept in physics called the light cone, and understanding it transforms how you see the universe. At any given moment, from any given location, there exists a boundary defined by the speed of light. Everything inside your past light cone, the region of space from which light has had time to reach you, is observable. Everything inside your future light cone, the region your signals can reach from this moment forward, is influenceable. Everything outside both cones is causally disconnected from you. It has not affected you. It cannot affect you. You cannot reach it. You cannot signal it. You cannot know what is happening there in any meaningful sense of the word now. The light cone is not a metaphor. It is a physical boundary as real as a wall, and it means that at any given instant, the vast majority of the universe is simply inaccessible. Not hard to reach, not expensive to reach, inaccessible. Disconnected from your location by the geometry of space-time in a way that no technology, no matter how advanced, can overcome. The light cone is not a prison that better engineering can escape. It is the shape of causality itself. For interstellar communication, The light cone imposes delays that make real-time conversation impossible across even modest distances. A message sent to Proxima Centauri at the speed of light takes 4 years and 3 months to arrive. If someone there responds immediately, the reply reaches Earth 8.5 years after the original message was sent. That is not a conversation. That is an exchange of letters between strangers who might be dead before the response arrives. Scale the distance to 100 light-years, a tiny fraction of the galaxy, and a single exchange takes 2 centuries. A message sent today would receive a reply that arrives in the year 2226. Every person alive on Earth when the message was sent would be long dead. The civilization that sent it might have transformed beyond recognition or ceased to exist entirely. Scale further. A message sent across the galaxy, 100,000 light-years, requires 100,000 years to arrive. The reply, if one is ever sent, arrives 200,000 years later. When the message was originally transmitted, anatomically modern humans had not yet left Africa. By the time the reply arrives, the species that sent it may have evolved into something unrecognizable, or gone extinct, or never existed in a form that could receive radio waves. Galactic-scale communication is not slow. It is geological. It occurs on timescales that dwarf the existence of entire species. And even this assumes the message arrives intact. Radio signals weaken with the square of the distance. A transmission powerful enough to be detectable across the room becomes undetectable across a city. A transmission powerful enough to reach nearby stars becomes indistinguishable from background noise across the galaxy. The inverse square law is relentless. Even a civilization that devoted the entire energy output of its star to broadcasting a single omnidirectional radio signal would produce a signal so faint at galactic distances that detecting it would require receiver dishes the size of planets. Targeted, narrow beam transmissions fare better but require knowing exactly where to aim, which assumes you already know where the receiving civilization is, which assumes a prior detection that has not yet occurred. The temporal observability filter hypothesis, formalized in recent research, quantifies this problem precisely. Even a megawatt transmitter, an enormously powerful signal by any standard, falls below the detection threshold of current and near-future instruments beyond roughly 100 to 125 light-years. The Milky Way is 100,000 light-years across. Our ability to detect artificial signals covers a sphere containing approximately 1/1,000,000th of the galaxy's volume. We are not scanning the cosmos for alien signals. We are scanning our immediate neighborhood and calling it a search. The combined effect of distance, speed limits, and signal degradation produces a picture that most people have never been asked to confront. Every civilization that arises in this galaxy, no matter how intelligent, no matter how technologically advanced, is physically confined to a tiny local bubble. That bubble is defined not by ambition or capability, but by the geometry of space-time and the behavior of electromagnetic radiation across cosmic distances. Inside the bubble, communication is slow but theoretically possible. Outside the bubble, communication ranges from impractical to impossible. And the bubble is vanishingly small compared to the galaxy it sits within. Imagine a concert hall so vast that its far walls lie beyond the horizon. A musician plays at one end. The sound leaves the instrument, crosses a few rows of seats, and fades into inaudibility long before reaching the middle of the hall. Another musician plays at the opposite end. Same result. Both are performing. Neither hears the other. The hall is not empty. It is full of music that never arrives. That is the galaxy. The players are real, the music is real. But the hall is too large for any performance to reach another stage. This is not a failure of will or imagination. It is not a problem that persistence can solve. It is a structural feature of the universe. The speed of light creates a maximum rate at which information can travel. The distances between stars ensure that this maximum rate translates into minimum crossing times, measured in years and decades and centuries. The rocket equation ensures that achieving even a fraction of the maximum speed requires energy expenditures that strain the resources of entire civilizations. And the inverse square law ensures that even light itself, the fastest and most efficient carrier of information in existence, becomes undetectable across the gulfs that separate most stellar neighborhoods. Each of these barriers alone would be daunting. Together, they form something closer to a verdict. The universe does not merely make interstellar contact difficult, it makes interstellar contact a problem of a fundamentally different kind than any problem humanity has ever solved. Every great journey in human history, every ocean crossed, every continent explored, every orbit achieved, operated within a framework where the barriers were large but finite. The ocean is wide, but ships can cross it. The atmosphere is thick, but rockets can escape it. These were engineering problems. Interstellar contact is not an engineering problem. It is a confrontation with the basic architecture of space-time, and space-time does not negotiate. You might think that time could rescue us. If the distances are vast and the speeds are limited, perhaps patience is the answer. Perhaps civilizations simply need to endure long enough, persist across millennia or millions of years, and eventually the slow crawl of signals and ships will bridge the gaps. Perhaps the universe rewards those who wait. But time, it turns out, does not help. Time is not the solution to cosmic isolation. Time is the final wall. And what it does to the problem of alien contact is perhaps the most devastating revelation of all. Everything we have covered so far assumed the most generous possible scenario. It assumed that two civilizations exist at the same time, that while one is transmitting, the other is listening, that the sender and receiver are both alive, both technological, both capable of recognizing each other's signals during the same window of cosmic history. It assumed, in other words, that the clocks of civilization line up. This assumption is so fundamental to every conversation about alien contact that it is almost never examined. It simply sits there in the background, invisible, load-bearing, and almost certainly wrong. To understand why, you need to feel the true depth of cosmic time. Not just know it intellectually, but feel it in a way that changes how you think about everything that follows. The universe is approximately 13.8 billion years old. That number is cited so frequently in popular science that it has lost its capacity to shock. So let us restore it. Compress the entire history of the universe into a single calendar year, with the Big Bang occurring at midnight on January 1st and the present moment falling at midnight on December 31st. On this cosmic calendar, the Milky Way forms sometime in late January. Our Sun and solar system do not appear until September 1st. For 8 months of cosmic time, our star did not exist. Earth forms in early September. Life appears almost immediately, microbial organisms taking hold by mid-September. But then something remarkable happens. Nothing. For months and months and months, life on Earth remains single-celled. Multicellular organisms do not appear until mid-December. Dinosaurs arrive on December 25th, Christmas Day. They dominate for several days before an asteroid wipes them out on December 30th. The entire history of mammals rising to prominence, primates evolving, hominids walking upright, humans developing language and tools and agriculture and cities, all of this takes place in the final hours of December 31st. Recorded human history begins about 14 seconds before midnight. The Industrial Revolution happens in the last second. The entire era of radio technology, our window of electromagnetic detectability, occupies roughly the final tenth of a second of the cosmic year. 1/10 of 1 second out of an entire year. That is the duration of our technological civilization compressed against the age of the universe. This is not a metaphor chosen for dramatic effect. It is a proportionally accurate representation of how brief we are. Now apply this understanding to the question of alien contact. For two civilizations to communicate, they must both exist during the same cosmic moment. They must both be in their technological phase simultaneously. The window of radio detectability for humanity began in the early 20th century. If we are optimistic and assume human civilization endures for another 10,000 years in a technologically communicative form, our total window of detectability spans roughly 10,000 years. Against a galactic history of 10 billion years, 10,000 years represents 1/1,000,000th of the available time. 1/1,000,000th. Imagine the history of the Milky Way as a single 24-hour day. Each civilization's communicative lifespan is a brief flash, a flicker. Ours lasts less than 1/10 of a second. Even a civilization that maintains technological communication for 1,000,000 years, a duration vastly beyond anything humanity has achieved or seems likely to achieve, would flicker for less than 9 seconds of that galactic day. For two such civilizations to overlap in time, both flickers must occur during the same moment. In a day filled with silence, two candle flames must burn simultaneously, and neither gets to choose when it is lit. The mathematics of this overlap problem are unforgiving. Suppose the galaxy has produced 10,000 technological civilizations across its entire history. That sounds like a generous number. 10,000 separate instances of intelligent life developing radio technology, or its equivalent, scattered across 10 billion years. If each civilization lasts an average of 10,000 years, the total time occupied by all civilizations combined is 100 million years. Spread across 10 billion years, that means at any given moment, the probability that even one civilization is active somewhere in the galaxy is roughly 1%. The probability that two are active simultaneously and close enough to detect one another drops far below that. And these calculations assume civilizations are evenly distributed in time, which they almost certainly are not. The real distribution is likely clumped. Stars form in bursts. Heavy elements, necessary for rocky planets and complex chemistry, accumulate gradually over galactic history. The earliest generations of stars contained almost no metals, making planet formation around them difficult or impossible. The conditions for life-bearing planets improved over billions of years as successive generations of stars enriched the interstellar medium with heavier elements. This means civilizations are more likely to arise in the second half of galactic history than the first. But even within that narrower window, the timing problem remains devastating. A civilization that arose 2 billion years ago and lasted 1,000,000 years has been dark for 1,999,000,000 years. Its signals have long since passed through our region of the galaxy and continued outward into intergalactic space. Its artifacts, if any survived, have been eroded by cosmic radiation and micrometeorite bombardment for eons. Its existence left no trace that we could detect today. It came and went in silence, surrounded by a galaxy that had no one to notice. But the ghosts do not vanish cleanly, and this introduces one of the most haunting dimensions of the timing problem, a dimension that transforms the empty sky from a simple absence into something closer to a cosmic graveyard filled with voices that no one can hear. When a civilization broadcasts electromagnetic signals, those signals do not stop when the civilization dies. Radio waves, once emitted, propagate outward at the speed of light in every direction, expanding as a spherical shell that grows larger with every passing year. The civilization that created the signals may collapse, destroy itself, evolve beyond recognition, or simply go silent. But the signals persist. They continue traveling through interstellar space long after their source has fallen dark. The electromagnetic imprint of a civilization can outlast the civilization itself by millions or even billions of years, depending on the power of the original transmission and the sensitivity of any potential receiver. This means the galaxy may be saturated with signals from dead civilizations right now, not signals aimed at us, not messages crafted with the intention of being received by a particular audience, just the electromagnetic residue of technological activity, the radio equivalent of waste heat, leaking outward from worlds where no one is home anymore. Television broadcasts, radar pulses, communication beams, navigation signals, all of the electromagnetic noise that a technological species generates during its active period, expanding in concentric shells through the interstellar void. These signals are real, they are physical. They carry information about civilizations that existed and fell silent before our solar system formed. And they are, almost certainly, undetectable. The inverse square law guarantees that as signals spread across light years of space, their energy density drops precipitously. A powerful broadcast that could be easily detected at a distance of 10 light years becomes billions of times fainter at 10,000 light years. By the time these orphaned signals reach regions of the galaxy where someone might be listening, they are buried so deep beneath the natural radio noise of the cosmos that no instrument could distinguish them from background static. The galaxy, then, is not silent. It is whispering. It is filled with the fading electromagnetic echoes of civilizations that rose and transmitted and fell, their signals still rippling outward through space at the speed of light, passing through star systems, washing over planets, carrying the last technological fingerprints of extinct minds across a cosmos that has no one left to decode them. If you could somehow amplify and filter the radio spectrum of the Milky Way to infinite sensitivity, you might hear not silence but a cacophony, a layered chorus of millions of dead civilizations all speaking at once, their transmissions overlapping and blending into an indecipherable murmur that stretches back billions of years. We cannot hear it. The signals are too faint, too dispersed, too ancient. But they are there, in principle, woven into the electromagnetic fabric of the galaxy like the fossilized imprints of creatures pressed into sedimentary rock. A record of intelligence that existed, spoken in a language of photons that no one alive can read. This electromagnetic graveyard reframes the silence of the cosmos. When SETI researchers point their telescopes at the sky and hear nothing, they are not necessarily hearing evidence that civilizations are rare. They may be hearing evidence that civilizations are brief. The signals exist. They simply originated too far away, too long ago, and from sources too faint to be distinguished from noise across the distances involved. The sky is not empty. It is archaeologically rich and observationally mute. The universe keeps a record of every mind that ever broadcast, but it writes that record in ink too faint for anyone to read. This chemical evolution of the galaxy introduces a spatial dimension to the timing problem that is rarely appreciated. The Milky Way did not become uniformly hospitable to rocky planets and complex chemistry at the same time everywhere. The inner regions of the galaxy, closer to the galactic center, experienced faster star formation, faster chemical enrichment, and earlier accumulation of the heavy elements needed for rocky planet formation. Stars in the inner galaxy had access to sufficient metals for terrestrial planet formation billions of years, before stars in the sparse outer arms reached comparable enrichment levels. This means the galaxy has a chemical geography of habitability that evolved over time. The inner regions likely became capable of producing Earth-like worlds several billion years before the outer regions where our solar system sits. If civilization-bearing planets require a threshold level of metallicity, which observational evidence strongly suggests they do, then the earliest possible civilizations would have arisen in the inner galaxy, perhaps 7 or 8 billion years ago, while the outer arms did not become chemically ready until 4 or 5 billion years ago, when our own sun and solar system formed. The consequences for the timing problem are severe. A civilization that arose in the inner galaxy 7 billion years ago existed in a chemical epoch that had not yet reached the Orion Arm. The stars in our neighborhood had not yet formed the rocky planets needed for life. By the time our region of the galaxy became chemically mature enough to host technological civilizations, that inner galaxy civilization could have been extinct for billions of years. The two were separated not just by distance, and not just by random temporal misalignment, but by the sequential chemical development of the galaxy itself. Different regions of the Milky Way pass through their windows of habitability at different times, like seasons arriving at different latitudes. Spring came to the inner galaxy while the outer arms were still in deep winter. By the time spring reached us, The inner civilizations had already lived through their summer and fall. This chemical timing gradient means that even if civilizations are common, the galaxy's own developmental history spaces them out in time as well as space. Civilizations in metal-rich regions near the galactic center may have peaked billions of years before civilizations in metal-poor outer regions became possible. The galaxy does not produce its experiments in intelligence simultaneously across its full extent. It produces them in waves dictated by the slow enrichment of the interstellar medium, spreading outward from the center over billions of years. Each wave is separated from the last by timescales so vast that no signal from one wave can reach the next while anyone from the earlier wave is still listening. And what about physical evidence? Signals fade, but surely objects endure. If a civilization built probes, megastructures, orbital installations, or modified the surface of a planet, those physical traces should survive long after the civilization itself has vanished. Archaeology works on Earth precisely because physical artifacts persist across millennia. Stone tools, pottery shards, building foundations, all of these survive for thousands of years and allow us to reconstruct vanished cultures. Should not the same principle apply on a galactic scale? If civilizations existed millions or billions of years ago, should we not find their ruins scattered among the stars? The answer, devastatingly, is probably not. And the reason is that deep time is not merely a longer version of historical time. It is a qualitatively different regime in which the very concept of persistence loses its meaning. Consider a metallic probe launched into interstellar space by an alien civilization 1 billion years ago. Over that span of time, the probe has been continuously bombarded by cosmic rays, each high-energy particle knocking atoms out of the probe's crystalline structure, gradually degrading its metallurgy at the atomic level. Micrometeorite impacts, each one individually microscopic but numbering in the trillions across 1 billion years, have pitted and eroded every exposed surface. The vacuum of space has caused volatile compounds to sublimate. Internal mechanisms have seized as lubricants evaporated, and thermal cycling stressed joints and welds across millions of heating and cooling cycles during close stellar approaches. Radiation has degraded any stored data beyond recovery, flipping bits, ionizing storage media, and scrambling every record the probe once carried. After 1 billion years, this probe is not a recognizable artifact. It is a small, irregular lump of partially crystalline metal drifting through the void, its surface pocked and roughened, its internal structure homogenized by radiation damage, its original shape lost to erosion. If a human telescope detected it, it would be indistinguishable from a metallic asteroid fragment, the kind of natural debris that populates the galaxy in countless trillions. There would be no way to determine that it was ever crafted by intelligent hands. The universe has sanded away the evidence with a patience that spans geological epochs. Larger structures face similar fates on longer timescales. An orbital habitat abandoned around a distant star would be gradually deorbited by gravitational perturbations from passing stars and giant planets. Its structural components would be stressed by thermal cycling, weakened by radiation damage, and eventually fragmented by micrometeorite bombardment. Over hundreds of millions of years, the fragments would be scattered into independent orbits, some falling into the host star, others ejected into interstellar space, each piece degrading individually into unrecognizable debris. A Dyson sphere, the grandest megastructure imaginable, would meet the same fate if left unmaintained. Without active station keeping, the gravitational dynamics of the host star system would destabilize its components within millions of years. The remnants would be absorbed, scattered, or destroyed, leaving no coherent signature detectable from interstellar distances. Even modifications to a planet's atmosphere, perhaps the most durable possible signature of technological activity, would be erased by natural geological cycling. Earth's own atmosphere is maintained in its current state by continuous biological activity. If all life on Earth vanished tomorrow, The excess oxygen would be consumed by geological processes within roughly 10 million years. Methane would disappear within decades. The atmospheric composition would revert to a geochemically stable equilibrium that bore no trace of the biosphere that had sustained it for billions of years. A civilization that engineered its planet's atmosphere would leave signatures that persisted only as long as the engineering continued. Once the civilization stopped, geology would quietly erase the evidence within a cosmically trivial time frame. The universe does not merely separate civilizations in time, it actively erases the evidence that they ever existed. Each new civilization arises in a galaxy that appears pristine, untouched, and empty, not because it has never hosted intelligence, but because the evidence of prior intelligence has been ground to dust by the patient machinery of deep time. The galaxy could be littered with the unrecognizable remains of 1 million technological species, their probes degraded to anonymous metal fragments, their megastructures scattered into orbital debris, their atmospheric signatures reabsorbed by indifferent geology. And we would never know. We would look at the sky and see exactly what we see now: silence, emptiness, and a cosmos that shows no trace of anyone who came before. This is the final turn of the timing problem's knife. Civilizations are brief, their signals fade below detection, their physical artifacts decay beyond recognition, and the galaxy resets itself between each experiment in intelligence, presenting every new species with the same blank canvas, the same apparent solitude, the same unanswerable question: are we the first, or merely the latest in a long line of minds that asked and never learned the answer? This is worth dwelling on because it overturns a deeply held assumption. When people imagine alien civilizations, they implicitly imagine them as contemporaries, beings who exist right now, in this century, looking at the same stars we see, grappling with the same questions. But the universe has no obligation to synchronize its experiments in intelligence. A civilization could have risen on a planet orbiting a star on the other side of the galaxy 500 million years ago, achieved technological sophistication that dwarfs anything humanity has built, transmitted signals across thousands of light years for 100,000 years, and then fallen silent for any of 1,000 reasons. War, environmental collapse, a natural catastrophe, simply losing interest in broadcasting. That civilization's entire communicative history would have unfolded and concluded hundreds of millions of years before the first proto-humans walked upright on Earth. We would never know it existed. We could not know. The evidence is gone. Now run this thought experiment in the other direction. 500 million years from now, a civilization arises on a rocky planet orbiting a young star in the Perseus arm of the Milky Way. They develop radio astronomy, they build telescopes, they scan the sky for signals, they listen for decades, for centuries, they hear nothing. Meanwhile, Earth has long since become uninhabitable. The sun has brightened by several percent, boiling away the oceans. Human civilization, whatever form it may have taken, ended billions of years ago. The beings in the Perseus arm will never know about us. Our signals, broadcast at the speed of light, passed through their region of space long before their planet even formed. We are to them a ghost that left no haunting. This temporal isolation is not a quirk of unlikely timing. It is a natural consequence of the numbers involved. The galaxy is old, civilizations are brief. Even optimistic estimates for the longevity of a technological species, measured in hundreds of thousands or millions of years, are small fractions of galactic time. And the window during which two civilizations can meaningfully interact, meaning they must both be active, both within communication range, and both using compatible detection technologies, is a tiny subset of an already tiny subset of cosmic history. Research published in astrophysics journals has attempted to formalize this problem. The concept of the contact era, introduced by astronomer Amri Wandel, defines the minimum time a civilization must survive in a communicative state before the probability of contact with another civilization becomes significant. The calculation depends on how many civilizations exist, how long they last, and how far apart they are. But the results are sobering under nearly every reasonable set of assumptions. Unless civilizations are extraordinarily abundant, numbering in the hundreds of thousands active at any one time, or extraordinarily long-lived, persisting in a detectable state for millions of years, the contact era for any individual civilization is measured in thousands to tens of thousands of years after the onset of transmission. Humanity has been transmitting radio signals for approximately 1 century. We are not in our contact era. We may not enter it for thousands of years, and even that optimistic estimate assumes we survive and continue broadcasting, an assumption that carries no guarantee. The Drake equation, that famous framework for estimating the number of communicative civilizations, includes a variable called L, the average lifetime of a communicative civilization. This single variable dominates the entire equation. If L is small, say a few hundred years, the galaxy is likely empty of detectable civilizations at any given time, even if life is common and intelligence evolves frequently. If L is large, say 1 million years, the galaxy might contain thousands of concurrent civilizations. But we have exactly one data point for L, ourselves. And our data point is incomplete because our civilization has not yet ended. We do not know how long technological civilizations typically last. We cannot know until we find another one, and we cannot find another one until our communicative windows overlap. The circularity is vicious. What limited evidence exists is not reassuring. Humanity has possessed nuclear weapons for approximately 80 years. We have been altering our planet's climate for roughly 2 centuries. We have created artificial intelligence systems whose long-term implications we do not fully understand. Every century of technological advancement has introduced new existential risks alongside new capabilities. The same technology that enables interstellar communication also enables self-annihilation. If this pattern is common among technological species, then L may be tragically short. A civilization that destroys itself after a few centuries of technological capability barely registers against galactic time. Its window of detectability opens and closes like the shutter of a camera, capturing nothing because nothing was passing by at that instant. But even setting aside self-destruction, the timing problem has another dimension that is rarely discussed. Civilizations do not merely need to overlap in time, they need to overlap in compatible technology. A civilization that communicates through gravitational wave modulation would be invisible to one listening for radio signals. A civilization that encodes information in neutrino beams would be undetectable by electromagnetic telescopes. Even within the electromagnetic spectrum, choices matter. A civilization transmitting at microwave frequencies would be missed by one scanning optical wavelengths. The assumption that all civilizations converge on radio as their primary communication technology is a projection of human development, not a physical law. The universe offers many channels. The odds that 2 independently evolved civilizations choose the same channel, at the same frequency, at the same time, while aimed at each other's region of space, are considerably lower than the already low odds of simple temporal overlap. This deserves more concrete attention because the technology compatibility problem is not abstract. It has sharp, specific edges that cut deep into the probability of detection. Consider humanity's own trajectory. We have been a radio-transmitting civilization for approximately 1 century. During that century, our transmission patterns have already changed dramatically. Early radio broadcasts were powerful, omnidirectional, and analog. The kind of signal that leaks freely into space and could, in principle, be detected by a sufficiently sensitive receiver at interstellar distances. But the trend of communication technology on Earth has moved steadily away from this pattern. Modern communications increasingly rely on fiber optic cables, which emit no radio signal into space at all. Wireless transmissions have become lower power, higher frequency, digitally encoded, and spread across wide frequency bands in ways that make them resemble random noise rather than coherent signals. A civilization observing Earth from 50 light-years away would see our radio signature brighten rapidly in the mid-20th century and then begin to fade as we transition to communication methods that are effectively invisible from interstellar distances. This suggests that the window during which a civilization is loudly radio bright may be startlingly short. Perhaps only a few decades, the brief period between the invention of powerful broadcast technology and the transition to quieter, more efficient systems. If this pattern is common among technological species, then the radio-detectable phase of any given civilization is not measured in thousands or millions of years, it is measured in decades. A civilizational eye blink so brief that the odds of two species being radio loud at the same time, within detection range of one another, collapse toward zero. But the compatibility problem extends beyond radio. Suppose an alien civilization bypasses radio entirely and develops communication technology based on modulated neutrino beams. Neutrinos pass through ordinary matter almost without interaction. A neutrino-based communication system would be extraordinarily difficult to intercept unless you knew exactly what to look for and had built specialized detectors for that specific purpose. Humanity currently operates neutrino detectors for pure research, not for communication, and their sensitivity is nowhere near sufficient to detect an artificial neutrino signal from another star system. If an alien civilization were beaming information at us via neutrinos right now, we would have no idea. The signal would pass through our planet, through our bodies, through our instruments, and continue into space without leaving a trace. Or consider gravitational waves. Since their first direct detection in 2015 by the LIGO Observatory, gravitational waves have opened an entirely new window on the universe. An advanced civilization might develop the ability to generate and modulate gravitational waves for communication, a technology that would be undetectable by anyone not specifically equipped with gravitational wave observatories tuned to the right frequencies. Our own gravitational wave detectors are designed to observe astrophysical events like black hole mergers, not to decode artificial signals. Even if such signals were present in the data, we would likely dismiss them as natural phenomena or noise. The deeper problem is epistemological. We do not know what we do not know. Our SETI searches are inherently constrained by the detection technologies we have invented, which are themselves products of our particular evolutionary and technological history. We search for radio signals because we invented radio. We search for optical laser pulses because we understand lasers. But an alien civilization with a fundamentally different technological trajectory might communicate using methods we have not conceived of, methods based on physics we understand, but have not applied to communication, or methods based on phenomena we have not yet discovered. Two civilizations could exist simultaneously within the same galaxy, even within the same spiral arm, both actively broadcasting, both desperately searching for signs of others, and remain mutually invisible forever because their detection technologies do not overlap. Each one is listening on a channel the other is not using. Each one is shouting in a language the other's instruments cannot hear. They are ships passing in the night in the most literal sense, each one's signal washing over the other's world without triggering a single detector, without generating a single data anomaly, without leaving even a faint suggestion that someone else is there. The combined weight of temporal misalignment, spatial chemical gradients, and technological incompatibility creates an isolation so thorough that it does not require any exotic explanation. No great filter, no dark forest of predatory civilizations, no zookeepers deliberately hiding from us. The ordinary operation of physics, chemistry, and the statistics of independent technological development is sufficient to produce a galaxy that feels empty to every species within it. Even if the galaxy has produced millions of civilizations across its history, the silence is not strange. Given the constraints, the silence is expected. What would be strange, what would require extraordinary explanation, is if we actually heard something. Now zoom out beyond our galaxy, and the timing problem does not merely persist, it metastasizes. The observable universe contains approximately 2 trillion galaxies. Many of these galaxies are vastly larger and older than the Milky Way. The total number of potentially habitable planets across all observable galaxies is a number so large it loses meaning. Trillions upon trillions of possible worlds. Surely, in all that immensity, civilizations must exist in abundance, and they might. But the observable universe adds a new barrier that operates on top of distance and on top of time, a barrier so fundamental that it transforms the entire question of alien contact. The universe is expanding. It has been expanding since the Big Bang, and that expansion is accelerating. Distant galaxies are not merely far away. They are moving away from us, carried by the stretching of space itself. The farther a galaxy is, the faster it recedes. At a certain distance, roughly 14 billion light-years, the recession velocity equals the speed of light. Beyond that distance, galaxies are moving away from us faster than light can travel. This does not violate Einstein's speed limit because the galaxies themselves are not moving through space at superluminal velocities. Space itself is expanding, carrying the galaxies along like raisins in rising bread dough, but the effect is the same. Light emitted by those galaxies today will never reach us. Signals sent from Earth will never reach them. They are causally disconnected from our location, sealed off behind a cosmic horizon that no technology can breach. This means the observable universe, the 93 billion light-year sphere we can theoretically see, represents only a fraction of the total cosmos. The rest is unreachable, not difficult to reach, not expensive to reach. Unreachable in the most absolute physical sense of the word. Information cannot cross the gap. Signals cannot bridge it. No matter how much time passes, no matter how advanced a civilization becomes, the regions beyond the cosmic horizon are permanently and irrevocably cut off, and the situation is getting worse. Because the expansion of space is accelerating, driven by dark energy, the cosmic horizon is effectively shrinking over time. Galaxies that are currently observable are being carried beyond the horizon by the accelerating expansion. In approximately 2 trillion years, every galaxy outside the local group, our small gravitational family of a few dozen galaxies, will have disappeared beyond the cosmic horizon. Future astronomers in the merged remnant of the Milky Way and Andromeda will look out at a sky containing only their own galaxy. The rest of the universe will have vanished, not destroyed, not dimmed, vanished. Carried beyond the reach of light by the relentless expansion of space. This means that the already narrow window for intergalactic contact is closing. Any civilization that might exist in a distant galaxy, broadcasting with unimaginable power across the void, is racing against an expanding universe that is slowly severing every connection between cosmic neighborhoods. Even at the speed of light, most signals sent between galaxies today will never arrive. The expansion outpaces the message. The letter is sent, but the postbox moves away faster than the letter can travel. It floats in transit forever, never reaching its destination, a permanent testament to the futility of calling out across an expanding cosmos. Within our own galaxy, cosmic expansion does not tear things apart on stellar scales. Gravity holds the Milky Way together against the expansion of space. Stars within the galaxy are gravitationally bound and will remain so. But the timing problem operates independently of expansion. Even in a gravitationally bound galaxy, civilizations that arise at different times in different locations face the same fundamental mismatch. The galaxy does not coordinate its experiments. A civilization in the Sagittarius arm does not wait for one in the Orion arm to be ready. Life ignites when conditions permit, burns for as long as conditions allow, and dies when conditions change. The universe runs 10 billion parallel experiments in civilizational development, each one blind to all the others, each one constrained to its own sliver of time and space. Consider the loneliest possible version of this scenario. The Milky Way, across its entire history, produces exactly 1 million civilizations. Each one endures for exactly 100,000 years, a lifespan far exceeding anything humanity has demonstrated. Spread uniformly across 10 billion years of relevant galactic history, these civilizations occupy a combined 100 billion years of detectability. That sounds like saturation, but it is not, because the civilizations do not pool their lifespans. They spend them one at a time in separate locations. At any given moment, roughly 10 civilizations are active simultaneously. 10 civilizations scattered across a galaxy 100,000 light-years wide. The average distance between any two concurrent civilizations is approximately 30,000 light-years. A radio message sent between them takes 30,000 years to arrive. A round-trip exchange requires 60,000 years. Each civilization's entire communicative lifespan is 100,000 years. During that lifespan, they can complete at most one full exchange with their nearest contemporary. One message sent and one reply received across the gulf, each carrying information that is 30,000 years stale by the time it arrives. One conversation in the life of a species, and even that single exchange is more likely to arrive after the sender has gone dark. This is not contact. This is not a meeting. This is two prisoners in solitary confinement, separated by miles of stone, tapping on pipes so slowly that each tap takes millennia to arrive. By the time a response comes, the original sender may have forgotten the question, or died, or evolved into something that no longer uses pipes. The exchange is theoretically possible. It is functionally meaningless, and this scenario assumed 1 million civilizations, a number that many estimates would consider wildly optimistic. Reduce the number to 10,000, a figure more in line with moderate Drake equation estimates, and the average distance between contemporaries increases to tens of thousands of light-years. Reduce it further, to 100, and the contemporaries are scattered so thinly across the galactic disk that each one occupies a sphere of silence extending across a significant fraction of the entire Milky Way. At 100 simultaneous civilizations, the nearest neighbor is likely so far away that even a single one-way message requires more time to arrive than the sending civilization will survive. Humanity's own radio bubble illustrates the scale of this isolation with painful clarity. We have been broadcasting electromagnetic signals for roughly 1 century. Those signals travel outward at the speed of light, forming a sphere approximately 200 light-years in diameter centered on Earth. This sphere, our electromagnetic footprint, the only evidence of our technological existence that any outside observer could detect, encompasses roughly 15,000 stars. That sounds like a meaningful number until you compare it to the galaxy. The Milky Way contains between 100 billion and 400 billion stars. Our radio bubble encompasses less than 100,000th of 1% of them. If an alien civilization existed on the far side of the galaxy and pointed its most sensitive instruments in our direction right now, it would see nothing. Our signals have not reached them. They will not reach them for another 99,000 years, assuming the signals remain detectable at such distances, which they almost certainly will not due to the inverse square law. We are invisible. Not because we are hiding, not because we are primitive, because light is slow and the galaxy is vast and we have only been shouting for a cosmic instant. The same is true in reverse. If a civilization on the far side of the galaxy began transmitting 100 years ago, its signals will not reach Earth for 99,900 years. If it began transmitting 10,000 years ago, its signals are still in transit, crossing the interstellar void at light speed, arriving in roughly 90,000 years. For all practical purposes, that civilization is as unreachable to us as if it existed in a parallel universe. Unlike the dead signals haunting the electromagnetic graveyard, these are messages from the living, which makes their inaccessibility worse, not better. The information about its existence is physically present in the electromagnetic spectrum, encoded in radio waves or laser pulses or some other carrier, propagating through space at the fastest possible speed. But the information is in transit. It is between us. It has not arrived, and by the time it does, we may no longer be here to receive it. This is the temporal prison. Not just distance. Not just speed. Time itself, the mismatch between the brevity of civilizations and the vastness of cosmic history, conspires to ensure that even a galaxy rich with intelligent life can feel permanently empty from the perspective of any single species within it. The silence is not evidence of absence. It is evidence of scheduling. The universe is not devoid of voices. It is devoid of simultaneous voices within earshot of one another. Distance builds the walls. The speed of light determines how slowly messages can crawl along them. And time ensures that even if the walls could be bridged, the beings on either side are almost never there at the same moment. 3 barriers, 3 independent mechanisms of isolation. Each one alone would make contact extraordinarily difficult. Together, they form something that looks less like a challenge and more like a sentence. Not a punishment imposed by a conscious universe, but a consequence of physical law so thorough, so layered, so deeply embedded in the structure of reality that escaping it may not merely be hard, it may be impossible. The question that remains is not whether these barriers exist, they do. The question is what it means to live in a universe that builds them. What it means to be a conscious mind in a cosmos that may produce countless other conscious minds, while ensuring that none of them ever touch. That question does not belong to physics. It belongs to something deeper. And it is waiting for us now. We have now walked through the 3 walls that the universe places between every mind it creates. Distance, measured in trillions of miles of empty vacuum between neighbouring stars and incomprehensible gulfs between galactic arms. Speed, capped at an absolute limit that no amount of technology or intelligence can exceed, turning even modest interstellar journeys into odysseys lasting decades or centuries. And time, the cruelest wall of all, ensuring that even in a galaxy producing civilization after civilization across billions of years, the odds of 2 technological species existing simultaneously and within communication range of one another are vanishingly small. Each wall is formidable alone. Together they do not merely make contact difficult, they make meaningful contact between independent civilizations one of the least likely events the universe permits. And now, we must face what this means, not as a physics problem, not as an equation to be solved, but as a truth about the kind of universe we actually inhabit, because the implications reach far beyond radio telescopes and rocket engines. They reach into something that humans have wondered about since the first members of our species looked up at a dark sky full of stars and felt, deep in their chest, that someone must be looking back. The instinct toward cosmic companionship is one of the oldest and most persistent features of human thought. Every civilization that has ever existed on Earth has populated the sky with minds. The Greeks placed gods among the constellations. Medieval scholars imagined angels turning the celestial spheres. Indigenous cultures worldwide described the stars as ancestors, spirits, living beings watching from above. When science replaced mythology, the impulse did not vanish. It simply changed costume. Gods became aliens. Celestial spirits became extraterrestrial intelligences. The specific narratives shifted, but the underlying emotional architecture remained identical. We are not alone, and the universe contains minds besides our own that are aware of us. This impulse is not irrational. It emerges from a cognitive system that evolved to detect agency, to assume that events have causes, and that causes often have intentions. When early humans heard a rustle in the grass, the ones who assumed a predator was hiding survived more often than the ones who assumed it was just the wind. Natural selection built brains that default to assuming minds are behind events. This hyperactive agency detection served us well on the savannah. But it also means that when we look at a universe teeming with stars and planets, our brains reflexively populate it with watchers, with thinkers, with beings who know we are here. The emotional conviction that someone is out there is not a conclusion drawn from evidence. It is a cognitive reflex, ancient and powerful, running beneath conscious thought. Science fiction amplified this reflex into a cultural certainty. For more than a century, stories about space have been stories about meeting aliens who are wise and benevolent. meeting aliens who are hostile and terrifying, meeting aliens who are strange and incomprehensible. The specific character of the meeting varies endlessly, but the meeting itself is never in doubt. Audiences have been trained, through thousands of films and novels and television episodes, to treat interstellar contact as the natural endpoint of cosmic exploration. The hero builds a ship. The ship crosses the void. The alien is there, waiting, ready to speak, ready to fight, ready to teach. The universe, in these stories, is fundamentally a social space. It is large, yes. It is dangerous, certainly. But it is populated, and its populations are reachable. This is the beautiful lie we described at the beginning. And now, having traced the physics of distance, speed, and time to their logical conclusions, we can see its full outline. The lie is not that aliens exist. They very well might. The evidence supporting the possibility of extraterrestrial life is stronger today than at any point in human history. Over 6,000 confirmed exoplanets, billions of estimated habitable worlds, organic chemistry woven into the fabric of the interstellar medium, life appearing on Earth almost as soon as conditions permitted, suggesting that biology may be a common outcome of the right chemistry in the right environment. Nothing in modern science argues against the existence of alien life. If anything, the trend of discovery over the past 3 decades has made the case for alien life steadily stronger. The lie is that existence implies meeting. The lie is the invisible bridge that human intuition builds between knowing that life might be out there and assuming that we will one day confirm it face to face, signal to signal, mind to mind. The bridge feels solid, it looks obvious, but it is constructed from nothing but hope and narrative convention, and the physics of the actual universe does not support its weight. What the universe actually offers is something far stranger and far more disturbing than either the optimist's dream of contact or the pessimist's fear of absolute solitude. The universe offers a third possibility, one that human culture has barely begun to grapple with. A cosmos that is alive but permanently disconnected. A galaxy that produces mind after mind after mind across billions of years, each one burning in isolation, each one surrounded by silence it cannot break, each one asking the same questions and receiving the same absence of answers, not because the answers do not exist, but because the architecture of space and time ensures they can never be delivered. This is the structural loneliness of existence. Not loneliness born from emptiness, loneliness born from separation. There may be a profound difference between a universe that contains no other minds and a universe that contains countless other minds but keeps them permanently apart. The first is desolate, the second is tragic. And tragedy, unlike desolation, carries a particular kind of weight. It implies that something valuable exists but cannot be reached, that the connection you long for is real in principle but forbidden in practice, that the universe is not barren but partitioned, divided into billions of tiny rooms, each one occupied, none of them adjoining. Consider what this means concretely. Right now, as you listen to these words, there may be a civilization orbiting a star 8,000 light-years away in the Scutum Centaurus arm of the Milky Way. They may have developed radio technology 3,000 years ago. They may have been broadcasting into the void for 30 centuries, pouring hope and mathematics and music into the electromagnetic spectrum, waiting for a reply that has never come. Their signals are real. Their signals are propagating through space at the speed of light, but those signals have covered only 3,000 light-years of the 8,000 light-year gap between us. They are in transit. They will not arrive at Earth for another 5,000 years. And when they arrive, if they are even detectable at that distance, there is no guarantee that anyone will be listening. There is no guarantee that human civilization will still exist. There is no guarantee that whatever species inhabits Earth in 7,000 years will have the technology or interest to detect a faint alien radio signal buried in cosmic noise. That civilization is real. Their loneliness is real. Their hope is real. And the universe has arranged things so that their hope and ours will almost certainly never intersect. or consider the opposite direction in time. Perhaps a civilization arose in our own galactic neighborhood, orbiting a star just 50 light-years away 1 billion years ago. They lasted 1 million years. They built wonders we cannot imagine. They filled their corner of the galaxy with art and thought and discovery. And then they were gone, extinguished by a gamma-ray burst or an asteroid impact, or the slow exhaustion of their world's resources, or the simple entropy that claims all organized systems given enough time. Their million-year reign ended 999 million years before the first multicellular organism appeared on Earth. They are separated from us, not by distance but by time, an abyss so deep that their entire existence fits into a sliver of geological history that left no trace we could hope to find. The universe did not prevent their existence. It did not prevent ours. It simply ensured that the two could never overlap. Two candles lit in the same room, but one extinguished 1 billion years before the other was struck. This reframing transforms the Fermi Paradox from a puzzle into a revelation. The question is not, where is everybody? The question is, when is everybody? And the answer may be that everybody is spread across 10 billion years of galactic history, each civilization occupying its own thin slice of time, each one surrounded by the silence of all the others who came before and all the others who will come after. The galaxy is not empty. It is a graveyard and a nursery simultaneously, filled with the echoes of civilizations that have already fallen silent and the unborn potential of civilizations that have not yet arisen. We happen to exist in our own particular slice, our own brief flicker, and from inside that flicker, the galaxy looks empty because we cannot see the flickers that do not coincide with ours. There is a version of this realization that slides toward nihilism, toward the conclusion that if contact is impossible, then nothing matters, that the cosmic isolation of intelligent life renders existence meaningless. But that conclusion does not follow from the evidence. It is an emotional reaction, understandable but not required. The structural loneliness of the universe does not diminish the value of the life it contains. It recontextualizes that value. If every civilization is a brief and isolated flame, then each flame is not less precious for being alone. It is more precious. The thoughts you are having right now, the consciousness hearing these words, the awareness contemplating its own place in a vast and silent cosmos. This may be among the rarest and most extraordinary phenomena the universe produces, not because minds are uncommon in an absolute sense, there may be billions of them across cosmic history, but because each instance of mind is unrepeatable, uncontactable, sealed within its own bubble of space and time, a unique experiment in awareness that the universe will never run in exactly the same way again. Humanity continues to search, and this searching is not futile. It is one of the most profoundly meaningful things our species has ever done. The James Webb Space Telescope, orbiting the Sun at the second Lagrange point 1 million miles from Earth, is currently studying the atmospheres of exoplanets, looking for chemical signatures that might indicate biological activity. Oxygen, methane, ozone, combinations of gases that should not coexist in an atmosphere unless something is actively producing them. The telescope cannot detect alien civilizations. It cannot image alien cities or intercept alien transmissions. But it can potentially detect the chemical fingerprint of a living world, a planet where biology has altered the atmosphere in ways that pure geology cannot explain. The planned Habitable Worlds Observatory, expected to be NASA's next great space telescope after Webb, is being designed specifically to image Earth-like planets around nearby stars and search their atmospheres for biosignatures. If funded and built, it will represent the most ambitious effort humanity has ever undertaken to answer the question of whether life exists beyond Earth. Not intelligent life, not technological life, just life. Microbes, algae, anything that breathes and metabolizes and changes the chemistry of its world. SETI continues as well, scanning the sky with instruments of increasing sensitivity and sophistication. The Breakthrough Listen initiative, funded with $100 million of private investment, is conducting the most comprehensive search for technological signatures ever attempted, surveying nearby stars, nearby galaxies, and the galactic plane for narrowband radio signals and pulsed optical transmissions that might indicate artificial origin. After more than 60 years of searching, the result remains silence. But the search has covered only a tiny fraction of the parameter space, a small number of stars, a limited range of frequencies, a brief window of observation time. The absence of a detection does not constitute evidence of absence. It constitutes evidence that the haystack is enormous and the needle, if it exists, is very small. These searches matter not because they are likely to produce contact in our lifetimes. They probably will not. They matter because they represent something essential about what it means to be a conscious species in an apparently silent universe. They represent the refusal to accept isolation without first testing its boundaries. They represent the decision to reach out even when the odds of a reply are vanishingly small. Every radio telescope pointed at a distant star is an act of defiance against the geometry of space-time. Every atmospheric spectrum analysed for biosignatures is a declaration that the question of cosmic companionship deserves an answer, even if the answer is silence. But we must be honest about what we are likely to find. Or rather, what we are likely not to find. If the analysis we have walked through is correct, if distance and speed and time together form a barrier that is structural rather than technological, then the most probable outcome of humanity's search for extraterrestrial intelligence is continued silence. Not because we are alone, but because the universe is built to keep its inhabitants apart. The silence is not a mystery to be solved. It is a feature to be understood. The cosmos is not withholding contact as a test or a punishment. It is simply operating according to its own physical laws, laws that happen to produce a universe where minds arise in isolation and remain in isolation regardless of how desperately they wish otherwise. This does not mean we will never detect evidence of life beyond Earth. Biosignatures in exoplanet atmospheres, if they exist, are potentially detectable with instruments that are being built right now. The discovery of microbial life on Mars, or in the subsurface oceans of Europa or Enceladus, remains possible and would transform our understanding of biology's prevalence in the cosmos. But detecting evidence that life exists somewhere else is categorically different from making contact with another mind. Finding alien bacteria is a biological discovery. Meeting an alien civilization is a relational event. The first is plausible. The second may be structurally impossible. And this distinction matters because it determines the emotional landscape of our cosmic future. A universe where we eventually discover that microbial life is common but intelligent life is unreachable is a universe that answers one question while deepening another. Yes, life is out there. No, you cannot meet it. Yes, the chemistry of biology is woven into the fabric of the cosmos. No, the minds that chemistry produces will never know each other. The loneliness is not resolved by the discovery of alien microbes. It is sharpened because it confirms that the universe is capable of producing life, that life is not a miracle confined to Earth, while simultaneously confirming that the distances and timescales separating instances of life are too vast for meaningful connection. There is a way to hold this truth without despair. It requires letting go of the expectation that the universe owes us companionship. The cosmos is under no obligation to be navigable. It is under no obligation to be social. It operates according to laws that produce stars and planets and chemistry and biology, with extraordinary generosity, and it operates according to those same laws in a way that separates the products of its generosity by impassable gulfs. Both of these things are true simultaneously. The universe is not cruel, it is not kind. It is structured, and its structure has consequences that we are only now beginning to fully confront. The terror, if we are honest, is not that aliens do not exist. It is that they might exist in abundance, and it does not matter. 10 billion civilizations could rise and fall across the history of the Milky Way, each one brilliant, each one curious, each one staring up at a sky full of stars and wondering if anyone else is out there. And every single one of them could live and die without ever receiving an answer, not because the answer does not exist, but because the answer is always in transit, always crossing the void, always arriving too late or too faint or too far away to be heard. Imagine a vast ocean dotted with islands. Each island supports a village. The villagers build fires on the beach, hoping the light will be seen by other villages on other islands. But the ocean is so wide that no firelight reaches another shore. The villages are real, the fires burn, the hope is genuine, but the ocean swallows everything. Each village lives and dies believing it is alone, never knowing that 1,000 other fires burned on 1,000 other shores across the same dark water. That may be the universe we live in, not an empty cosmos. A full one, full of life, full of minds, full of fires burning on shores too distant to see. The silence we hear when we point our telescopes at the sky is not the silence of a dead universe. It may be the silence of a living universe whose architecture prevents its inhabitants from ever confirming each other's existence. We are here. We are conscious. We are asking the question. And the question itself, the act of wondering whether anyone else shares this dark sky, may be among the most significant things any arrangement of matter has ever done in the history of the cosmos. The answer may be that we will never know, that the universe allows the question but withholds the answer, that the deepest loneliness is not being alone, but suspecting you are not alone and being unable to prove it. The stars are still there, billions of them, each one a possible sun to a possible world. The planets are real, the chemistry is real, the potential is real, but the distances are also real. The speed limit is real. The brevity of civilizations against the depth of cosmic time is real. And together, these realities compose a universe that may be the loneliest place imaginable, not because it is empty, because it is full of things that can never touch. That is the terrifying truth. Not that aliens are impossible, but that the universe may be built, from its foundations to its horizons, to ensure that no two civilizations ever confirm each other's existence. A cosmos that creates mind after mind after mind, scatters them across 100 billion light-years of expanding space, and lets each one burn alone, not out of malice, not out of design, out of structure, out of physics, out of the simple, implacable geometry of a universe that allows life but may never ever allow meeting. The fire burns on our shore tonight. We do not know if anyone sees it. We may never know, but we lit it anyway, and perhaps that is enough. Perhaps the act of reaching out into a silence that may never answer is itself the most extraordinary thing a small, brief, lonely civilization can do. We are here. We looked up. We asked the question. And the universe, vast and silent and full of unseen fires, continues without reply.